All right, you were right, Richard. These were pretty tough questions for Caroline. So a very good morning to you. Thwaites Glacier. I mean, there are plenty of studies that have been done on Thwaites Glacier. Too many to, and even now I still discover that I didn't know of. But they show exactly the bedrock control on grounding line retreat on the glacier. And some studies show that it's irreversible, that it may already be initiated or not initiated, that there is a tipping point, that there is no tipping point. So there is quite some diversity in all those different studies. All in all, if you look at it, it's the timing and the rate of the irreversible retreat that depends on a number of factors, which are the initial state and the imbalance, the current imbalance of your ice sheet, the processes that you include or not include or consider, and the magnitude of the forcing. And this little inset of Vio's paper shows the wide spread of uncertainty in different scenarios. And this uncertainty is due to exactly when is the timing that, for instance, this glacier, Thwaites Glacier, or the West Antarctic ice sheet in general is starting to collapse. We're not going to answer that question. I'm going to answer the question how far instead of when and how fast. So that means that where, in theory, we can the grounding line be stabilized and where it can be stabilized or where not, it cannot be stabilized, and this using quasi-steady state numerical analysis of, test whether you have a marine ice sheet instability. And then also recovery tests for the transient grounding line retreat, so taking a transient experiment in which we have a certain imbalance and then stop the forcing, and then check a bit whether early warning indicators, as Sebastian Roger has used, whether they can be useful as information. So for that, we're going to use the Corey model. It's a follow-up of Fetish. So what is new is that it can cope with basins at a higher resolution. We use a 2-kilometer spatial resolution. And we have used present-day surface mass balance from RACMO. And then Pico ocean model that we use as the ocean thermal forcing, in which we use a thermal exchange velocity as a tuning parameter in the analysis. So MISI, marine ice sheet instability, normally if you test this, you start with a steady state ice sheet, and then you perturb that system, and you try to find a new steady state. And then, here for the one-dimensional case, so absence of buttressing, you clearly see that over a retrograde slope that you have an instability, so no steady state solutions, and this leads to hysteresis. So Sebastian Roser has applied a similar thing like this on Pine Island Glacier. It's a quasi-steady modeling in which we start here from a steady state solution of the whole system of Thwaites Glacier. Here you see a zoom of this. In which we have a steady-state grounding line, so the ice is not moving anymore. I mean, the ice sheet is not changing anymore. And then we apply very small changes in perturbation for a given time. So it's quasi-steady state, so it's not full steady state, but like a long period of 200 years with a very small perturbation and C, and then always increasing this. I translated this perturbation here in terms of subshelf peak melt near the grounding line. So you start with very low values of this peak melt at the grounding line between 10 and 15 meters per year. And then gradually this increases, and you see that the grounding line retreats, as this figure also shows, until you reach a point, and then it just goes away. And that's where we have our tipping point. Of course, you can also return. The fact is that working here on this basin with these typical boundaries, it's very difficult to go all the way to a new steady state after the hysteresis. This is not the whole Antarctic ice sheet that is simulated. We can only do it from starting from that last stable point. And then also we should do it for a longer time spans to see whether you fully recover these grounding line positions. So the hysteresis is not fully evaluated. And then we can also do the transient modeling. So this is, you have a transient state, so there's a certain forcing, and the grounding line retreats. And then after a certain time, we stop altogether the forcing. So no melting underneath the ice shelf at all. And then we see what happens. And so in most cases, it just continues and moves away, and it also collapses. That is where you end up with 0.3, which is not shown on the figure to the right. But for instance, in this example here, after 80 years, it goes away, and then after 75 years, and that is the other, it's the light blue line or cyan, I don't know, I'm colorblind. So the near one, from there we reach a new steady state, and that is the steady state is given by number 2 there. So it's small changes in when you stop the forcing allow you either to stabilize or to go away. Now try to understand this. So not only to see how far, but say how deep. So what does this do? How does the grounding line ice thickness look like in all these experiments? So first of all, we did this here for the little dots. This is for the steady state experiments in which we gradually increase the forcing. And then we see that we have I calculated here the mean grounding line thickness for that section where we observe the retreat and the maximum ice thickness. And you see that, you come here towards the end to an area where you are above 1,250 meters as a maximum ice thickness, and the median ice thickness in this section is 825. You see that we made a jump here, and it's from this jump on that it moves away to much, then we have the collapse. And if you look at the transient run, and that is quite intriguing, despite that it's a transient and not a steady state, we find similar limits. So that's those here for the median and for the transient, so the red and the blue. And so that shows that it's a control, it's a depth of the grounding line that will tell you when this will happen. So, early warning indicators, that is only the beginning phase of looking at this. And I'm not sure whether it will work for Thwaites Glacier, because basically what happens is that this is the signal that we have of the unstable retreat, and from here it moves on very fast. We have the collapse. But basically, this is already a retreat that is already, that is unstoppable. I mean, despite whatever you can do. So if we don't take that into account, normally we should start here, only consider this area, but then the indicators show nothing. So I should have not shown this slide because it's completely non-informative. What we see in all these experiments that I did is that we have a same pattern. And the same pattern of retreat. So these are all the unstable retreats, and here they move all away. And you see, despite the initialization that you have, you see several areas where you have a little local stabilization. This is all locally, all these grounding lines, they are more or less in the same position. So you have, it's also, what has been shown by other authors, very bedrock controlled. And of course, if you use another bedrock topography or you increase resolution, these things may probably be slightly different. So, as a conclusion, we can identify a safety band for marine ice sheet grounding line positions in a sense that if you look for steady state positions. You can identify these steady states and therefore also a tipping point. The thing is that these steady state positions, both recoverable in a transient or from pure steady states, you can find them only in an area of less than 40 kilometers from the present day grounding line. So this is not a very big safety band. But it means that if we know the imbalance, if we know the forcing, if we know a grounding line position today and in near future, we may use that information to identify whether we approach a tipping point or how far we are from a tipping point. And that may help us maybe to better, fix when the when question and the how fast question by using the how far result. Thank you.
Thanks, Frank. We've got a couple of minutes for questions if anyone has one.
Yeah, Heiko, you had to put your hand higher.
Thanks, Frank. Really interesting talk. I'm wondering if you'd care to engage in any wild speculation about how much this 40-kilometer threshold might vary around the entire continent.
That's a question for Kenny with rings. But no wild speculation. I don't know, honestly. The thing is that if you take Pine Island Glacier, and that is what Sebastian has also shown, you have much more buttressing. You have several tipping points that exist there because of that topography. With Thwaites, it's a bit, it goes easy. You see here the forcing. I have both Pine Island and Thwaites. You see that Pine Island needs a bit more to get kicked further than Thwaites. So Thwaites needs a bit less. But of course, this experiment, I removed all scales. So there's no time scale on this, and it's done on purpose. I will not tell you. Because it depends on all these factors, how fast the how fast depends on the processes, depends on the forcing, and so on. But unfortunately, I cannot answer your question.
All right, I think Heiko had another question.
Okay, thanks, Frank. I'm just confused about your second takeaway, because if I understand well, you're saying that there's this thickness threshold. So shouldn't this be included in this takeaway? So that it's not like a XY position, but a XYZ right. position?
Yeah, you're right. You're definitely right. Yeah. Sorry about that.
Great, thanks. Lots of questions for Frank afterwards. We've got to move on.
Oh yeah, we have a lunch break for that.
All right. Next up, we've got Tim van der Akker talking about the precursors of glacier collapse in the Amazon.